Hi, today we're going to continue talking about atomic structure, specifically electron structure, and jumping headlong into the complexities of sublevels and orbitals. Looking at yesterday, at the previous information from the last presentation, we'd said that the Bohr model falls apart when dealing with multi-electron systems, and that really is illustrated quite well by these two lines right here. We had said before that, based on our previous discussions, that the violet line in hydrogen would be a transition from, say, energy level 6 to 2, and that the red line would be like 3 to 2, and the 4 to 2 and 5 to 2 there. But this also kind of suggests that there is a large energy difference between each of your principal energy levels. Oh yeah, I circled the E, pointed the E by mistake. When you get into these more electron systems, multi-electron systems, the energy levels, the colors, get a lot closer. So this would be a very close energy distance. And the Bohr model doesn't really allow for energy levels that close together that would give off energies that are still visible light. That might happen more in the IR or something like that. We needed a more complex description of how the electrons in multi-electron systems slot into the atom. And the answer was arrived at through a number of scientists. I cannot remember their names off the top of my head, but they are some names. Hund is one of them, and maybe this is where Pauli gets involved. But to take a look at the absorption spectra of several elements, the absorption spectra being the opposite of the emission spectra, where instead of bright lines we have a rainbow with certain lines subtracted as the atom absorbs them. It was noticed that there were several types of bars that showed up. We had the sharp, fine lines, but then we also had things that looked more like bars or bands, and they got named based on their appearance, which then got shortened to S, P, D, and F. Turns out that there are more than 4 sublevels. We then moved on into G, H. We skipped I because there's enough I's in other places, and then J, K, L. But as of now, no atoms exist that have ground state electron configurations that utilize G, H, and J sublevels, so we don't really talk about them too much. But I do want to talk about the sublevels that we do know about. There are 4. They're called S, P, D, and F. And when you are referring to a sublevel, it being a division of a principal energy level or shell, you refer to it by numbering the energy level and then giving that letter. So for example, 1s, 4f, 2s, 3p, 4p. It's possible to have several s sublevels in the same atom. And these s's are the spheres that we saw from the previous lesson, this being 2s, and this being 3s, and this here being 4s. What we have here are the 3 orbitals of the p sublevel, and each of these being a solution to the wave equation from Schrodinger, of course. This would be 2p, and this would be an example of 3p, both of them. And then we've got some d sublevels here and some f's. You see the 2 lobes, the 4, and the 6. And the idea is that these electrons all slot into these, and for each energy level, n, there are n sublevels present, and we always go in that order of S, P, D, F, G, etc. So you can only have 1 sublevel for the first principal energy level, only 2 for the second, 3 for the third, and so certain ones that you might hypothesize exist don't. The ones that exist being 1s, and then 2s and 2p, and then 3s, 3p, and 3d. Since these sublevels can contain 1 or more orbitals, that changes the number of electrons that fit into each sublevel. The numbers are given here. It goes up by 4 each time. I'm not going to worry too much about that because we're not worrying about orbital notation today. That'll be next. The biggest change with incorporating sublevels into our model of the atom is how we refer to the electrons and how they fit into the atoms. I'm going to go back at the end to describe why we saw the lines that we saw. But we can take the Bohr notations from the reference table, there's a link above my head, and translate them into what the sublevel notation would be by just filling electrons into the same order that we just described. The idea being, 1s, 2s, 2p, 3s, 3p, 3d, etc. So for the Bohr notation, we know that there are two electrons in the first energy level, so both of them would slot into the 1s2. We're labeling the 1s sublevel, 2 electrons fit into it, the 2 is written as a superscript. And then the next electron would be put into the second energy level, the first sublevel being s, and there's one of them. So to put it all together, 1s2, 2s1. As the atoms get more complex, it gets a little bit more difficult, but not terrible. The first 2 electrons again go into 1s2, the next 8 into 2s2, 2p6, and the next 3 into 3s2, 3p1. And when writing the electron configuration, you just string it all together. You don't need any spaces. That's why we have large numbers and then superscripts to help separate. But then as soon as the atoms do get larger in number, things get a little bit more complex. If you want to figure out bromine on your own, you can do that. But I will now. This comes out to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5. And as you can see, the electron configuration gets far more complex as soon as you start accounting for sublevels, but it does also provide a little bit more information for the things that we were observing. These bands of light that occur in close energy to each other, we kind of see that happening here for these elements. These close energy transitions happen when sublevels get involved. So we learned about hydrogen, this was a transition from energy level 3 to 2. But looking at similar energies, you might assume that maybe this is a transition from 3s to 2s, or from 3p to 2s, or from 3p to 2p. In terms of energy, these sublevels are very, very close in energy compared to the principal energy levels. If we go back to our graph of energy increasing, 2 would be well away from 1, but the 2 sublevels of 2 are very close in energy. So when you're making those transitions, the energy is very, very close in number, which means a very, very close set of lines in terms of your spectrum. And then, 3 would be somewhat above, and there'd be 3, and then it would go from there. Thanks for watching.